What's going on, guys? It's the Unhinged Engineer here, and today I'm very excited to talk about programming languages in aerospace engineering. So in the modern day, just about all kinds of engineers are coding, they're using computers. This is not a surprise to any of us. But for aerospace specifically, I've found it often difficult to determine which languages are used in which context, because honestly, a lot of times aerospace is different from other industries. And so today, I thought I'd break it down for you for anybody who's interested in getting into aerospace engineering, and specifically on the software side, which is where I've spent just about the entirety of my career. I'm the Unhinged Engineer. I make professional development content for young engineering professionals like myself. I'm an aerospace engineer by trade, but I also make content relevant to anybody looking to land their dream job, lead an awesome career, do cool stuff, make tons of money. You know the drill. So if that's stuff you're interested in, definitely like, comment, and subscribe. But without further ado, let's start talking about programming languages. Table of contents. I'm going to start off just talking about when aerospace engineers code. Obviously, again, we're all using computers these days, but what are the specific contexts in which aerospace engineers are coding the most, and what titles do those people typically have, so that if we're looking for jobs in a certain area, we can look to that job title, look to job recs with that same title, and then kind of reverse engineer a tech stack that will help us get where we're trying to go. After that, I'm going to get into the three biggest ones I've seen throughout my career, which are C++, MATLAB, and Python. And through talking about these three titans of industry, I'll be able to highlight not only what are the specific aspects of these languages that make them kind of the lingua franca, but also what are the different niches that they each fill in different ways. And again, we can start to think about how we'll slot ourselves into those niches using these tools. And then last but not least, I'll just kind of lay out a super preliminary roadmap of if you're starting from square one, like literally don't know how to code at all, where should you get started learning to code oriented towards aerospace engineering. So let's start off with which aerospace engineers actually code. So again, like I said, just about all of us are coding in some way or another, whether it's data analysis or plotting. Lots of pre-existing tools we use like SolidWorks, like CFD software, Simulink, which we'll talk about. A lot of them kind of have scripting within them. And then last but not least, automation. If we're doing either bullet points 1 or 2 a lot and we just want to automate that process, will also involve coding. So these are kind of the generic ways in which just about all of us are coding these days in some way or another. But beyond the basic stuff, what are the aerospace engineers that actually code? And the way I think about this is, who are the people whose job it is to produce software? So I am benchmarked for my promotions and pay and everything against the code I produce, both in terms of quantity and in terms of quality. Versus, maybe I'm a test engineer or a mechanical engineer. The scripting and things are just serving to support the other functions I fulfill, like producing CAD models or running FEA on those models, etc. But these people I'm talking about, it's their job to produce software, and that definitely would include me. So to start off, I'm going to talk about GNC. So GNC is a topic I've discussed a lot on this channel, but it basically stands for guidance, navigation, and control. And effectively, these are the algorithms on the aerospace vehicles that we're developing that manage how it guides the trajectory throughout its environment, whether that's a drone or a boat or a satellite. How do I actually chart a course that I want to follow throughout the course of my operation, whatever that may be. Navigation is how do I determine whether I'm on course, where I am with this environment, are there any obstacles around me, stuff like that. And the control is, okay, I know where I'm trying to be, that's guidance. I know where I am, that's navigation. How do I get from A to B? So how do I close that error? A lot of times it's going to involve physical control services like flaps or thrusters or whatever else. That's the control side, right? So figuring out those control inputs that are going to get us to the state that we want. All of this is GNC, and GNC involves a lot of really cool, really badass algorithms, and all those algorithms have to be coded somehow. So GNC engineers produce a lot of code. Now, the only people who probably produce even more code than GNC engineers are flight software engineers, right? And these are people who are writing embedded software that specifically runs on the vehicle. So what do I mean by this? On the GNC example I just provided, you're going to be running these algorithms in lots of different ways. You're going to be running them in simulation to determine, is this going to get us the behavior that we're looking for? Then maybe you start to run it with hardware in the loop, testing out basic components. So as an example, if I'm trying to write a control system for a drone and that control system is going to determine the signal I send to motors, maybe you want to test it running on those actual motors, pulse width modulate the voltage you're sending to them, and then determine, okay, in physical reality, am I actually getting the control output that I expected from my control input? That's kind of hardware in the loop testing, and there's lots of other forms. But ultimately, the software that's going to run on the vehicle, in the air, out in the ocean, in space, wherever, That's embedded software written by flight software engineers. So emphasis on flight, right? These are the people who are writing the software that's going to run on these vehicles. And the one I just described would be operating the vehicle itself, but that could also include stuff like telemetry and communication. A lot of these vehicles, they have to communicate with operators or even one another in today's very autonomous world. All that software that's running on the vehicle, that's flight software. And then last but not least, mod and sim. Modeling and simulation engineers are effectively building tools to help functions 1 and 2. So this is a role I have held before, I consider it a support role. All these different software algorithms and functionalities have to be modeled and have to be tested in some way. And these simulation tools are what mod and sim engineers build. So whether that's validating that the system is behaving a certain way, whether it's validating that a mission that we've determined is what we want to do, is that actually capable given the technical specifications of our vehicle or our ability to operate that vehicle in the field. So actually validating mission plans that functions 1 or 2 come up with. To me, these are the functions of aerospace engineering that write the most code. There are lots of other examples, like avionics engineers are a great example, but to me, just over the course of my career, subjectively, these are the 3 I've seen write the most code, and I'm kind of going to orient this conversation around them. Now let's get into languages, right? So the meat and potatoes of this video. What are the languages that these aerospace engineers, among the other ones that we'll talk about, use the most? And the 3 I'm going to just lay it out up front are C++, MATLAB, and Python. And they all serve different functions. You're going to see why momentarily. So first one here, the Goliath, C++. So C++ is the lowest level language that most aerospace engineers are going to use. Now, if you're a flight software engineer and you're watching this video, you're probably screaming right now because flight software engineers write base C, they write Verilog and VHDL for running on FPGAs. They do lots more embedded stuff that's really, really low level. To me, at that point, and by the way, I have done some entry level stuff in this area, like very, very low level. To me, that kind of digs down beneath aerospace engineering and really gets into computer engineering and even electrical at times. So if that's what you're interested in, then definitely learn C++, and C++ will kind of be the highest level language that you learn because you're going to be diving way, way deeper in the hardware stack than that. But for the rest of us mere mortals, right, who are aerospace engineers who are writing software not just to run on the vehicle and control it in flight, but also do stuff like algorithm development and simulations and whatnot, C++ is generally the lowest level that we're going to go. So the lowest level of abstraction here means the most control, performance, and danger. So what I mean by lowest level is that you're deep within the kind of guts of the computer. You're manually laying out stuff like how memory is laid out and accessed, what control flows we're using in terms of processes and threads and stuff like that, whether we're using flash memory or RAM or storing things on disk. Like, these are all very, very low level considerations that many other languages we'll talk about, like Python and MATLAB, don't really tend to get into. They kind of abstract that stuff away and have tools on the back end that handle that for you. C++ has no such luxuries. You're doing all of this yourself, and what that means is you can squeeze the most performance out of any given hardware platform, but the counter to that is if you're not careful, you can really shoot yourself in the leg and get in lots of trouble because you don't have the rails on like in a bowling alley. It's completely free game, and thus it's really up to you to make sure that you're operating memory and threads and processes, stuff like that, in a safe manner. What are the reasons why C++ is used so ubiquitously in aerospace engineering? For one, that real-time performance is really, really important for just about all the applications we talked about when laying out the different titles of engineers who write code. Flight software, obviously, it's the most important, but even for GNC algorithms, because a lot of these algorithms are going to ultimately run on the vehicle. So the idea here is like if a GNC engineer is going to write these algorithms, they should probably write it in something that's at least somewhat close to the hardware. You have a GNC engineer who knows the algorithm, you have a flight software engineer who knows the software stack and the hardware beneath it, and together you can write an algorithm that really, really performs well on vehicle. That's actually the next bullet, so I skipped ahead here. But yeah, transitioning C++ to embedded software like C or other things is less opaque than other languages like Python. So naturally, because C++ is a low-level language and is derived from C, there's a lot of legacy software and hardware that is geared best towards C++ or C. Because Python and MATLAB and other tools are so much newer, it's harder to make them backwards compatible with those applications and that hardware, and thus C++ has a really strong legacy aspect to it. Last but not least, as I alluded to in the beginning, that explicit memory management, type conversions, linking to different libraries and stuff makes for predictable and safer code, right? So I'm writing safer here to mean that you can tell what the software is going to do. It's very traceable. It's very human interpretable. But when you have stuff in Python where types are obfuscated from the user and the Python language has some kind of logic on the back end that does auto conversions for you, when you have stuff like garbage collection that willy-nilly just kind of cleans up memory whenever processes are done, when you have all these language abstracted features, you get less explicit understanding of how the language is going to behave at any given moment. Now, if you're a rocket, or especially a missile or something, you really want to know how it's going to behave at all times. You don't want any undefined behavior. And thus, C++ puts that onus on the engineer. So they say, okay, I'm going to give you total control, and in exchange, you have the responsibility of controlling the software, controlling this memory, linking libraries, handling type conversions, whatever, explicitly. So it's all on you if something goes wrong. If something blows up, it's your fault, right? Because you determined exactly how that software is supposed to behave in every single edge case. That's the core idea of writing flight software or GNC algorithms in something like C++ as opposed to something nice and fun and easy like Python. All right, now let's talk about MATLAB. So C++, for the most part, was geared towards algorithm development, flight software, and simulation. But MATLAB is a very, very ubiquitous tool in aerospace engineering, primarily for simulation. And something I'm going to allude to here, it's really the go-to in school, and not just for aerospace engineering, but also for mechanical and electrical. Just about every engineering student who goes to a school that has a MATLAB license, you're going to write crap tons of MATLAB in school. There's several reasons for this, but one of the reasons I think is that MATLAB, to me, is a really powerful scripting tool that allows you to do very complex simulations of complex physical or electrical phenomena without having to deal with all the thorns of C++ like we just discussed. So all those different facets of a very, very low level of abstraction, that's really difficult to teach someone. And so when you're an aerospace engineer or mechanical engineer or whatever, and your primary goal is not to learn coding, but coding is a really, really useful tool for learning about some of the physical phenomena that you're going to learn in school, like heat transfer, like dynamics, like electrical circuits, whatever. MATLAB kind of fills this like middle ground really, really well, and thus you're going to see it a ton, which you'll see when I talk about where should you start in terms of an aerospace engineering coding education. So what are the reasons that it's so ubiquitous? For one, it facilitates really rapid prototyping. So you can write up scripts to simulate different things and by extension validate different designs, algorithms, etc. really, really quickly in MATLAB. And a lot of the reason for that is really the IDE, not just the language of MATLAB itself. The MATLAB IDE and the full package that's kind of sold to you by MathWorks is really, really integrated and has less ancillary things you have to get done as opposed to if you're writing raw C in Vim, right? Speaking of rapid prototyping, Simulink is this really, really strong low-code tool. So again, when we're educating people, low code is good to ease them into the water. So with Simulink, instead of writing explicit code, you're laying out block diagrams and saying, okay, I want this kind of transfer function here and this kind of input and then plot the output in this way, and different things like that. You can plug and play different system types, which again, on the back end, MATLAB is simulating in a decently performant way. You can do all of that yourself at this higher level of abstraction that's not even coding, and thus you can get really good expressivity in terms of prototyping different things without having to write a ton of code. Speaking of that, when we do some kind of simulation or system validation, whatever you want to call it, a lot of times you have to parameterize that in some way. So it's not enough to just test in one environment, in one configuration, in one setup. You have to parameterize inputs and dynamics well in order to determine it's not just going to work well in this nominal case, it's going to work in just about any of the cases I could expect. And so again, like MATLAB has lots of really good tools for saying, okay, I have this one script that's kind of my baseline, and I'm going to fuzz it in different ways to say, okay, does it work in this condition or that condition or where this thing breaks, et cetera, et cetera. All those different types of parameterization, MATLAB is really, really well suited, again, for some of the reasons I alluded to earlier. Believe it or not, MATLAB does actually have really good tools for transitioning to embedded software that, again, can run on a flight computer, on a microcontroller, in our actual aerospace vehicle. So it's not as close to the hardware as something like C++, but again, MATLAB, because it's like one organization and one product, does have a ton of tools to help you take what's written in MATLAB and push it as far to something that can actually run on the hardware as you possibly can go. And a lot of times, that road leads through C++ or a C language in general. So yeah, so MATLAB is not actually as bad of a starting point for something like flight software as you might initially think, given how it's geared towards students and it has lots of ancillary tools and a nice GUI and stuff like that. You actually can get pretty low, believe it or not. Speaking of that, there's a very, very large suite of tool sets, extensions, etc. MATLAB has a really strong community of mostly companies, actually, right? Like companies, universities, stuff like that. And these different groups contribute tools to MATLAB. And a big part of this is actually that the organizations and the professors can profit off of these extensions, right? Because if other people use these extensions, MathWorks is benefiting a lot because more people are on their platform and they actually give a kickback to the people who develop these toolboxes, right? So it's kind of this like pseudo open source for-profit setup, which is pretty interesting. I've heard MATLAB extensions are big money, but anyway, there's a lot of tools for stuff like RF, for stuff like control systems, for stuff like crazy hypersonic thermal phenomena, machine learning, for anything that you could really use a specific toolbox of individual tools developed by somebody with a specific subject matter expertise. MATLAB is probably going to have it. And this is how they keep people in this ecosystem. It's really, really interesting. They have an interesting business model. Effectively, if you develop some kind of vehicle and one day you wake up and say, oh my goodness, I have to look at electromagnetic interference that the antenna on the front of it might be experiencing. I don't have to go somewhere else and get someone else to write a bunch of software from scratch. I can just pull in this extension from the MATLAB marketplace ecosystem, and right away I can run it on the same exact simulation that I've done all the other fancy stuff from. I've written it in Simulink, I've parameterized it in different ways, and I've deployed it to flight computers. You get what I'm trying to get at. The unified ecosystem is really, really strong and surprisingly diverse, which is cool. Next one, Python. So Python is kind of the challenger in the industry. Despite being one of the most common, most ubiquitous programming languages in computer science writ large, within aerospace specifically, it's actually kind of on the front end of that adoption curve. And one of the big reasons is that young people like ourselves are starting to age out of school and get into the workforce. And despite the fact that MATLAB has tried really, really hard to build a monopoly on engineering education, it's really hard to compete with free and open source. And so naturally, when people are doing programs in their free time, or maybe they don't go to a university that has access to a pretty expensive MATLAB license, people are using Python. And thus, as people like us age into industry, Python itself is becoming much more common. What are some of the reasons why Python is actually a pretty good disruptor to the aerospace industry in terms of code? Well, for one, like I just said, it's more accessible than MATLAB. Simple enough. Beyond that, you can actually get a lot of the C++ functionality by wrapping C++. So a really common paradigm is you write a bunch of simulations in C++, and then you wrap that code in Python. So you're running C++ for real on your computer, but the programmer themselves is actually controlling it with Python. And that means that you get the performance of C++ with the ease of use of Python. Python's biggest strength in any capacity is how easy it is to write. And so if I can get some of that C++ performance, or almost all of that C++ performance, and just wrap that library in Python, and on my day-to-day, when I'm coming into work and I'm pulling out my computer, I don't have to write C++ every day, which is pretty difficult. I just have to write Python. That's huge. And naturally, this has become a very common paradigm for GNC and simulation work. And speaking of that, Python is actually the gold standard for AI ML development with tools like PyTorch, TensorFlow, etc. And the reason for this, among many, is that these toolboxes actually follow that wrapping paradigm. So when you run PyTorch code, you're writing everything in Python, you're laying out your models, you're doing stuff like that. And then what's running on the back end is C++, or if it's on a GPU, it's CUDA, which is similar but built for parallelization. You're running this very high performant, very low level abstraction piece of code in C++ or CUDA, but you only have to write Python, which is way easier and way more readable for other developers. This is a pretty good setup that a lot of companies have started to adopt it, both in aerospace and in the AI/ML field. So all of this kind of coalesces to make Python this really strong, challenger to legacy aerospace languages like C++ and MATLAB. Okay, so now that we've laid out all the coding languages that aerospace engineers use the most, if you're starting from square one, where do you begin, right? What do you learn first? I want to lay out like a super preliminary roadmap for anybody who's interested in aerospace engineering, specifically on the software side, and doesn't know where to begin. The first question I want to ask is whether or not you're new to coding. This is a very straightforward question. If you've never coded before, just start with Python. It's the most accessible, it's the easiest to begin, and Python, to be fair, despite it being very, very easy to pick up, it is pretty hard to master. And so you can learn a lot just from writing Python all the time. And again, like lots of AI ML engineers who are doing crazy algorithms and stuff, they're writing all that in Python. So just because Python's easy doesn't mean it's a bad language to start with, and that you have to race to C++ right away. You don't have to do that. Start with Python. It'll make your life so much easier and make it fun, which is ultimately what's going to lead to that habit of coding sticking and then getting you where you're trying to go. Okay, so let's say you're not new to coding. Either you've been writing Python for a while, or you've even been writing languages that are more difficult than Python, and you're trying to gear your skill set towards aerospace engineering more. Well, the next question here is, what are you interested in? If you're interested in flight software or GNC, you gotta learn C++. There's no way around it. C++ is the language that you will be expected to know to perform that job. It's gonna be hard, it's gonna be challenging, but something I will note here is that C++ is used for the reasons I talked about previously. It gives you a lot of control over the hardware, and thus you can get a lot of performance out. I would say more than anything, even more than learning the specific syntax of C++, beyond just a base competency level, the most important thing to learn through C++ is that actual core functionality, those core concepts of computing that C++ allows you to leverage. And that's when you really start to see the magic happen of writing really performant algorithms and even deploying it to flight software. Okay, quick caveat here. If you're not new to coding, and even if you know a little bit of Python, if you're interested in machine learning, or in this context of aerospace, autonomy, GNC plus AI/ML gives you autonomy. If you're interested in this field, you definitely gotta learn some more Python, and specifically PyTorch and TensorFlow, like the AI/ML toolkits built within Python that, again, wrap C++. I would highly, highly advise getting to a really advanced level of Python if you're interested in stuff like autonomy and machine learning stuff, computer vision, etc. But let's say you're not interested in flight software, GNC, or even simulation, and you're not trying to be an autonomy engineer. You're just interested in aerospace engineering in general. My last question for you is, what are you studying, assuming you're going to college here? If you're studying a physical engineering field, like mechanical, electrical, or aerospace, which is what I studied, I would advise getting some C++ knowledge here. And the reasons for this are kind of weird. You'll see in the CS point, I'm picking languages I think you should learn kind of in a complementary way. So if you're studying a physical engineering field, chances are you're going to write a ton of MATLAB for school. So you're going to learn MATLAB anyway. And thus, I think some basic understanding of C++, which is, again, the most performant language that is used in aerospace engineering overall, you're going to learn some really cool computing concepts that can actually be used in stuff like Python or MATLAB, again, at that high level of proficiency. So I would advise that every engineer should at least learn a little bit of C++, or at a minimum, the foundations of computing that C++ allows you to leverage that make it so desirable. Now, by contrast, if you're studying computer science and you're doing a lot of C++ and Python, I would advise actually going out and learning MATLAB if your school has access to a license. So once you get out, MATLAB licenses aren't cheap for individuals, and they're the most cheap when you're in school, because usually it's free. I would actually take that opportunity to learn MATLAB, but not just for the tool itself, but also similar to C++ teaching you computing knowledge, MATLAB shows you how to write simulation software, which is kind of an interesting type of software application. Like, it's not like most where there's this user interface and there's requests between different parts. It's very weird where you kind of wind up all these equations of motion, right? And you have these dynamics and then solvers for certain things within that dynamics, like whether you're doing a control system or path planning or whatever. Like, simulation software is pretty different from other types of software applications that any other CS major might write. And thus, getting some experience with that, either in MATLAB, which is kind of the tool that most of your peers in school are going to be using if they're mechanical or aerospace or whatever else, or Python, if that's all you have access to. Python is still great for simulation for some of the reasons we talked about earlier. Learning one of these scripting languages as opposed to a compiled language like C++ can be really, really fruitful for you. And so I advise, again, those recommendations at the end with college are kind of complementary. If you're doing a lot of MATLAB in school, go out on your own and learn C++. And if you're doing a lot of C++ in school or focusing on computing a lot in school, then go off and learn MATLAB and write some cool sims with toolboxes or whatever. Okay, guys, that's basically it. Today, I just wanted to lay out what coding languages are used the most in aerospace engineering by aerospace engineers and why. So again, you can do just about anything you're interested in any of these languages, and there's lots of other languages that are worth learning that just might be a little bit less widely adopted in aerospace. Some come to mind, like Rust, JavaScript and TypeScript for front-end stuff, Julia for scientific computing, Go. There's lots of different languages out there, and you can do just about anything you want in just about any of them. But I wanted to write this video to kind of highlight some of those general trends within aerospace engineering of different companies, stacks, and ultimately the skills that you can learn that are going to be the highest leverage. They're going to get you the kinds of jobs you want and allow you to transfer from company to company or from internship to internship. So I hope you enjoyed this video. I'm the Unhinged Engineer. I make professional development content for young engineers like myself. I'm an aerospace engineer by trade, but if you're interested in professional development, leading an awesome career, making a lot of money, building cool stuff, working at awesome companies, if you're interested in learning all those bits and pieces of leading a good engineering career that you don't actually get taught in school, then this is a channel for you. So thanks a lot for watching. Please like, comment, subscribe, and I will see you next time.